Welcome to lesson 1 of 1 in this tutorial, covering series and parallel circuits. This is our only video on the topic of current, voltage and resistance. Here are the key learning objectives for this session. We'll start with series and parallel circuits, move on to cover resistors, and then looking at investigating resistance in experiments. We'll also cover short circuits. Here are the AQA specification points for this section. Feel free to pause the video now and read through them before we begin. We'll start with the ways in which we can join electrical components. There are two main types of circuit. These are series circuits and parallel circuits. In a series circuit, all the components are connected in line with each other, as shown here. In parallel circuits, the components are connected in separate loops, as shown here. Some circuits will have both series and parallel parts. Now let's look at our next learning objective, covering the differences between the two types of circuits. On the left, we have a parallel circuit, where the components are said to be connected in parallel. On the right, we have a series circuit, where the components are said to be connected in series. You should be able to draw and recognise these two types of circuits in exam questions. Next, we'll look at using circuit diagrams to check series and parallel circuits. Again, we can see an example of a series circuit, an example of a parallel circuit. In these, we can see that there is a switch, several lamps, and ammeters in each circuit. Our next specification point deals with the current through components in series. In a series circuit, there are a few rules we need to remember. The first is that the current will be the same in all parts of the circuit. This means the current can be calculated by dividing the voltage of the battery or the cell by the total resistance in the circuit. We also need to know about the total potential difference in series circuits. In a series circuit, the total voltage is shared amongst the components. In this example, the circuit has lamps of varying resistances. The total voltage here is 6 volts, and this is shared between the lamps. The higher the resistance of the lamp, the larger the voltage across it. It's really important that you remember the total voltage used by the three components equals 6 volts, which is the same as the voltage supplied by the cell. Here is an example of a different circuit. Here, there is only one lamp, so it gets the full share of 6 volts supplied by the cell. Let's move on to our final specification point for this section of the tutorial, covering the resistance of components connected in series. The total resistance is the sum of resistances of all the components. If you add an extra lamp to a series circuit, the total resistance increases and hence the current decreases. All the lamps present will become dimmer. In this diagram, as we explained before, the lamp with the highest resistance will get the highest share of current. We can use an equation here, which is voltage is equal to current times resistance. We need every lamp to have the exact same current. In this diagram, things are a little bit simpler. There is only one lamp with a resistance of 2 ohms. Therefore, the current is 6 volts divided by 2 ohms, which gives us an answer of 3 amps. The lamp gets the full voltage of 6 volts. The total resistance is defined as the sum of the resistances of all the components. We can also define it using this equation, which is total resistance is equal to resistance 1 plus resistance 2. Here's the short version, which will be quicker for you to write out in the AQA exam. We're only dealing with resistances here, so the units will be ohms. We've met this before. You should make sure to practice lots of questions involving multiple resistors before your exam. This is a very commonly asked question. Next, we should know that the cell voltages will all add together. In this diagram, the voltages of the 3 lamps add up to 6 volts, which equals the voltage supplied by the cell. Students often find it hard to get their head around circuits, so let's just recap things once more and have a look at a few circuits. In this circuit, the voltage of 6 volts all goes to this single lamp. We can work out the current as shown here. Here we have a different circuit. The 6 volts is split between the 2 lamps of equal resistance. They're both going to get 3 volts each. However, adding the extra lamp has made both the lamps dimmer. The brightness depends on the current. Let's calculate the current. We can use the same formula again, which is current is equal to the voltage divided by the resistance. This leaves us with 1.5 amps. Here's another circuit. The 6 volts is now split between 3 lamps. They all need to have an equal current, so the voltage is split relative to the resistance. The 4 ohm lamp will carry half the total resistance, which is 8 ohms, so it gets half the voltage, which is 3 volts, whilst the other 2 lamps will get 1.5 volts each. Let's calculate the current again. We can use current is equal to V over R. This means that 6 over 8 will give us 0.75 amps. Here, our voltage has been doubled to 12 volts. Therefore, each lamp will get a double voltage. Let's calculate the current again. Here, we can see that it's 12 over 8, giving us an answer of 1.5 amps. Our next rule is that if there is a break in one component, this will ruin the whole circuit. For example, Christmas lights are often used in series circuits because each bulb only needs a small voltage, so it's better to share the voltage in series. However, like shown here, if one bulb breaks, then the whole circuit will break. Here's a summary of what we've just learned. You should take a note of this, as it will be useful for your revision. We've now covered all the learning objectives for the first section of our lesson today. Feel free to skip back through the video and re-watch any of the sections you feel unsure about. Here is our next set of AQA specification points for this lesson. Feel free to pause the video now and read through them before we carry on. We'll start by looking at the potential difference across components connected in parallel. In a series circuit, the voltage was shared between the components in proportion of their resistance. In parallel circuits, the voltage will be the same for all the components. This means every component is going to get the full maximum voltage. In this circuit, there are 2 lamps connected in parallel, receiving 6 volts from the cell. Now let's look at the effects of parallel circuits on current. The current will be split between the branches of the circuit. The sum of the currents of all the branches will be equal to the total current that flows from the battery. In this circuit, the current is split between the 2 branches. The cell supplies a current of 3 amps, but it has been split into 1 amp and 2 amps. contrast to series circuits, if there is a break in a parallel circuit, this will not ruin the whole circuit. Lighting in our houses is often connected in parallel because it means we can control the different branches of the circuit, which are often in different rooms, using switches. If the bulb in the second branch is broken, as shown here, all the current will now be diverted through the first branch. Our next specification point looks at the effects on resistance. The total resistance is worked out using the reciprocal of the resistances of each branch. We've just seen how to define total resistance. We can also work it out using the following equation, which uses the reciprocals as described in the previous slide. Here's a short version, which is easier for you to use in an exam. The units are still ohms. You don't actually need to know this equation off by heart for AQA exams, but we've included it here for you to become familiar with, in case you need to use it. Here's a quick summary for the rules for parallel circuits. Now let us look at how adding resistors in series and parallel will be different. Here is a series circuit with one resistor. Resistors make it difficult for the current to flow. With two resistors, it is even harder for the current to flow. This is because the overall resistance has increased. In a series circuit, adding resistors will increase the resistance. The current is the same in every single component in the circuit, so the more resistors we add, the harder it will be for the current to flow. Things are slightly different in a parallel circuit. Here's a parallel circuit with one resistor. When there are two resistors in the parallel circuit, there will be a decreased overall resistance. In a parallel circuit, adding resistors will decrease the resistance. The potential difference is the same in every single component in the circuit. The more resistors we add in parallel, there are more pathways for the current to go through, so it's easier for the current to flow through the circuit. This means the overall resistance will decrease in the circuit. You don't need to know how to perform the calculations with the rules we've just covered. You just need to know how to describe them and understand what they mean. It's important you get used to handling questions which have more than one resistor joined together in series. Our next specification point will focus on calculations. For AQA exams, we need to be able to calculate the combined resistance, also called the equivalent resistance, of the resistors. Don't worry, you only need to be able to do this for resistors in series. Resistors in parallel will not be tested. Now, we will look at solving problems in circuits including resistors. Let's have a go at this practice question. Here is the answer. For this question, we need to remember that the term equivalent resistance simply means the total resistance of the resistors in the circuit. Therefore, we've used our equation to add together the value of 20 ohms and 10 ohms. Now let's fill in this table as a summary comparison. First, we'll look at voltage in series circuits. Here, the voltage was shared amongst the components. In parallel circuits, all the components get full voltage. In terms of current, the current will be constant in a series circuit. In a parallel circuit, the current will be split between branches. Now let's look at resistance. In a series circuit, the total resistance will be equal to the sum of the components. In a parallel circuit, it will be equal to the sum of the reciprocals. Now let's look at how breakages affect series circuits. In a series circuit, it will affect the whole circuit. In a parallel circuit, it will only affect the components in the same branch. Finally, let's discuss some examples. In a series circuit, an example would be Christmas lights. A parallel circuit example would be house lighting. Let's look at our final specification point for this lesson, covering the design of DC series circuits. For AQA exams, we need to design and use series circuits. We can investigate resistors using these circuits. First, we set up our circuit. Next, we have to check our circuit. We can now measure the PD of the working circuit. Our fourth step is to measure the current using an ammeter. Now we can use our equation to calculate the resistance of the circuit. As we carry on the experiment, we need to change the quantities of the resistors before we repeat steps 2 to 5. Here's the table of results that you should fill in. Using these results, we'll be able to plot a graph of quantity of resistors against total resistance. Since this is a series circuit, as more resistors are added, the total resistance should increase. Here's a useful summary of the experiment we've just learned. It's a good idea for you to take a note of this for your revision. Some exam questions may include a bar chart. You need to be able to interpret data from any kind of graphic representation. The specification asks you to be able to design this experiment, so you might need to be able to write out the method we've just described. This might take the form of a 6-mark question, so don't take these experiment sections lightly. For experiment questions, it's always good to draw out a template table, like the one we showed a few slides ago. It shows clearly how you will fill in your results. Less than 5% of candidates do this when asked to write out a method, so it will make you stand out. We can also investigate resistors in parallel. The experimental process is essentially the same. You don't actually have to know how to explain an experiment to investigate resistance in parallel, but they could give you a scenario with it. In other words, they can't have a 6-mark question asking you to design an experiment, but they can give you a scenario with the setup explained to you. This is an example of application questions. You should have learnt the experimental setup for series, so they want to see you apply your knowledge to a less familiar scenario. Short circuits occur when the current takes the shortest route with the least resistance. In this diagram, the current will prefer to pass through the plain wire than the lamps, because the plain wire has a lower resistance. Therefore, a short circuit is formed. When the switches are open, the current will go through the bulb and make it light up. For this kind of circuit, there is no parallel split in current. If the plain wire path is available, then all of the current will go down that pathway. Let's attempt this question now. Here's a step-by-step explanation for it. The resistance through the 10 ohm resistor must be half of the 20 ohm resistor, so the current will be doubled. Then we can use our equation to find the voltage. Let's have a go at this other practice question. The answer will be shown on the next slide. The first answer is false. When switch P is closed and Q is open, the current in the circuit will only be 2 amps, and only lamp B is lit. This is incorrect. The other answers are all true. Which of the following is a unit of voltage? The correct answer is coulombs times ohms divided by seconds. This is because current is equal to charge over time, and voltage is equal to current times resistance. Therefore, we just have to substitute current in the V equals IR formula. Which of the following statements are true? Only A and B are true. In a parallel circuit, the voltage is not shared, in contrast to a series circuit. Each branch will get the maximum voltage, making A true. B is also true because each branch of the parallel circuit will act like its own mini-series circuit. Different branches will have different currents, but within each branch, the current will be constant. C is incorrect because only the bulbs in the same branch will be affected. D is also incorrect as the reciprocal of the resistance is the sum of the reciprocals of the individual resistances. Here's our final practice question. The correct answer is F. When switch Q is closed, the current will bypass A, B, D, and E. The pathway through Q is the path of least resistance. The resistance in the circuit is quite low because only lamp C is involved. This is a series circuit in effect. Therefore, lamp C is very bright. When switch Q is closed, the current is now split between the 3 branches of the circuit, like a normal parallel circuit. All the lamps will become lit when the switch is open. A, B, D and E are brighter than before as they now receive a current. C is now dimmer than before because the total resistance in the circuit is higher as there are many lamps involved. You don't need to do a calculation here. If more lamps are involved, the resistance will inevitably be higher. Although some of these multiple choice questions are unlike your normal GCSE questions, they are still a fantastic way to revise and make sure your knowledge is perfect. We've now covered all the specification points for this tutorial. Feel free to skip back through the video and re-watch any of the sections you are unsure about. We've now completed Lesson 1.